So in this work, we basically address the problem of prediction in a spatial point process. So suppose we observe events along a space as per some underlying intensity function, and our goal is to predict counts y in a given region x dash. And we also want to produce intervals capital lambda of x in units of counts per unit area so that we can have validity as described in equation 1. Well, intervals produced by traditional parametric models are not valid if the assumed model class is wrong. But in this work, we want to produce intervals that will be valid even if the model is misspecified. So in our approach, we assume space to be discretized into R regions, which converts the event data into region and count pairs from some unknown distribution. And we want to now learn a conditional distribution for counts given regions. We assume the Poisson model class for the counts in every region where the mean is parameterized by theta. We define the loss as the per sample KL divergence, and the best model is the one that minimizes this loss. Now suppose somehow from the data, using some criteria, we learn a model theta hat. Then you can use this model along with the conformal prediction frameworks to produce intensity intervals that are valid even under model misspecification. But to get intervals that are tight and informative, you need a criteria that will give you a loss at theta hat which is close to the optimal loss. So we propose the following criteria, and this criteria leads to this provable out of sample accuracy guarantee. So we can prove that the loss at theta hat learned using equation 3 would be close to the optimal loss according to equation 4. And this theorem basically leads to tight intervals. So here we have a case where we generate count data using negative binomial distribution for 3 different intensity functions, and the data in this region is missing. So you can see that the average interval size for the proposed method in blue is 4 times less than the average interval size produced by maximum likelihood. Moreover, the empirical coverage is greater than the set 80% coverage probability for all the intensity functions. Here are some examples in 1 and 2 dimensions where we can see that the interval size also grows in missing regions to reflect the inherent uncertainty. So we basically propose a method for producing valid intervals using a Poisson model class which has an out of sample accuracy guarantee, and both guarantees are valid even under model misspecification. For more details, you can look at our paper. Thank you.